Now we come to the exercise 27, some theorem, Monar's theorems. So what's the states the statement? See, if f of z is continuous, if f of z is continuous function in a domain D, and if for every closed counter, C in the domain D, so integral of C f of z dz equal to 0. See this statement. If f of z is continuous function in a domain D, and if for every closed counter C in the domain D, integral of C f of z dz equal to 0, then f of z is analytic within D. F of z is analytic within D. See, we come to this, the proof. Let z not be a fixed point and z be a complex variable point inside the domain D. See, z not be a fixed. Suppose we take a unit circle, we fix as z naught and z be complex variable point inside the domain. Z be complex variable point lies inside the domain D. The value of the integral to z naught to z f of t dt is independent of the curve joining z naught to z. This is the values of the integral. So integral of z naught to z f of t dt is independent of the curve joining the point z naught to z and depend on z only. That depend on z only. So that is we write f of z equal to integral of z naught to z f of t dt. F of t dt is independent of path joining the point z naught. So we can write, so capital of f of z equal to integral of z naught to z f of t dt. So I'm going to take a point. If you take a point, let the z plus h be the point in the neighborhood of a point z. So if we take a point z, what's the neighbor of z? I take that point z plus h. So z plus h is a neighbor of the point given point z. So z plus h be point in the neighborhood of a point z. Such so I take a function f of z plus h minus f of z. So that is, if you take integral of z naught to z plus h f of t dt minus z naught to z f of t dt. So if you take this is f of z plus h minus f of z equal to integral of z naught to z plus h f of t dt minus integral of z naught to z f of t dt. So evaluating. So integral of z naught to z plus h f of t dt. So reverse the order of the integrations we get. So plus z to z naught f of t dt. So this is the one of the properties of a definite integral. We can write z naught to z plus h z to z naught. We can write this is equal to integral of z to z plus h. This properties of integral z to z plus h. We write integral of z to z plus h f of t dt. So we come. If we take absolute values f of z plus h minus f of z divided by h minus f of z is equal to 1 by h times of integral of z to z plus h f of t dt minus f of z. So is equal to, if we take this is a constant value, I take outside 1 divided by mod h of integral of z to z plus h f of t minus f of z dt. So integral of z to z plus h f of t minus f of z dt. So this is less than or equal to 1 by mod h integral of z to z plus h absolute values of f of t minus f of z dt. Suddenly this value suddenly less than or equal to epsilon by mod h into mod h. So this is the term. So this is the values. So mod h get cancelled. Suddenly this value mod f of t minus f of z suddenly made strictly less than epsilon for mod t minus z less than delta, because this is continuous of f of z. Therefore, that is absolute values of f of z plus h, absolute values of f of h, z plus h minus f of z divided by h minus f of z made very small. That value should be epsilon, which tends to 0 as epsilon tends to 0. Which tends to 0 as epsilon tends to 0. So thus limit h tends to 0, f of z plus h minus f of z divided by h minus f of z equal to 0. That is, we can write this. I take f of z this side. This is the definition of derivative of f of z. This is definition of derivative of the. So limit h tends to 0, f of z plus h minus f of z divided by h. We can write limit h tends to 0. This is derivative of f of, means derivative of this, suddenly this f of z equal to derivative of f of z. This is suddenly this is something. We write f dash of capital F of z equal to f dash of z. So thus the derivative of f of z exists, and so f of z is analytic in D. So derivative exists, f of z is analytic in D. But we know that the derivative of analytic function is analytic. We know that the derivative of analytic function is analytic. So the derivative f of z, that is f of z, is analytic in D. So the derivative exists, suddenly the function is analytic. So we come to one more this Morales theorems. What is the necessary and sufficient condition for f of z? So if a necessary and sufficient condition for a function f of z to possesses an infinite integral is a simply connected domain D. An infinite integral is a simply connected in a domain D is that the function is analytic in D for the any two independent integral differ by a constant. So indefinite integral, any two indefinite integral differ by a constant. First, if you prove, let f of z possesses indefinite integral f of z, so that f of z possesses indefinite integral f of z, so that f of z is integral of a to z f of t dt. So again here f of t dt is independent of path and curve. So suddenly we write f of z is integral of a to z f of t dt. So to prove that f of z is analytic, so by using again derivative of f of z equal to f of z, showing that f of z possesses derivative of f of z. F of z possesses derivative of f of z. Also, the derivative of analytic function is analytic. So this is the main. Derivative of analytic function is analytic. It follows that f of z is analytic. So derivative exists, the analytic function is. So that is also derivative of analytic function is analytic. It follows that f of z is analytic. Converse is if and only if the conversely, suppose that f of z is analytic in a domain D. To prove that f of z possesses an indefinite integral. So f of z possesses an indefinite integral. Let z naught be a fixed point and z be an arbitrary point in D. So fix z naught and z be an arbitrary in a domain D. That is, we say f of z is equal to integral of z naught to z f of t dt. F of t dt. We write. Now, so for the integral f of z along a curve D, joining z naught to z in the same to prove as the theorem 8 derivative of f of z equal to f of z. This prove f of z possesses indefinite integral given by 2. Possesses indefinite integral by 2. So second part is say let f of z and g of z be a two indefinite integral of the same function f of z. If we take the second part, if capital F of z and g of z be a two independent integral of the same function f of z, such we write derivative of z equal to f of z is equal to derivative of g of z. So that is, we say derivative of z is equal to derivative of z equal to, simply we can write d by dz of f minus c. That is, so this should be E0, means d by dz of f minus z equal to f minus z equal to 0. That is, integrating, we get f minus z equal to c. If you integrate, derivatives get cancelled. Derivative is a inverse process of integrations. So derivative get cancelled, f minus z equal to some integral constant c. So this we get, this is the complete proof. So f of z is along the curve D joining the point z0 to z. So same as the proof in first we prove in derivative f of z equal to f of z. This is C. F of z possesses indefinite integral. So in the second we take two function f of z and g of z. F of z and if we take a two function f of z and g of z is indefinite integral. We take a derivative f of z should be equal to derivative of g of z. I denote f of z. So d by d of f minus z. So derivative should be appear as 0. If we integrate it, we get integral constant c. So it is this. We covered one more in the Morse's theorem. So Morse's theorem is stands in a complex analysis. It is used in almost any argument that involve a non-algebraic construction of holomorphic functions. This is the tools for complex analysis. It is used in almost any argument that involves a non-algebraic construction of a holomorphic function. For example, suppose that I say f1, f2, etc. is a sequence of holomorphic functions converging uniformly to a continuous function f. On open disk by Cauchy's theorem, we know that the closed disk integral of c fn of z dz equal to 0. For every value of n along any closed curve c in the disk, then the uniform convergence implies that the closed path c f of z dz is equal to integral of closed path c. If we take a limit n tends to infinity, fn of z dz is equal to limit n tends to infinity closed path c fn of z dz equal to 0. So for every closed curve c, and therefore by Morse's theorem, f must be holomorphic. This fact can be used to show that for every open disk, I denote the disk should be a mu of certainly less than or equal to c. The set A of mu for all bounded analytic function, that is such that for analytic functions that u tends to mu tends to c is a Banach space with respect to supremum norm. With a supremum norm. So infinite sum and integrals. Morse's theorem can also be used in conjugation with Pipin's theorem and Weierstrass M test to show the analyticity of a function. Defined by sum or integrals, such as Riemann zeta function. So zeta function of z, so z of a should be equal to summation 1 run pump into infinity, summation n run pump into infinity, 1 by n raised to p. Or gamma function, we take a gamma function. Gamma of alpha is equal to integral of 0 to infinity x to the power of alpha minus 1 e to the power of minus x dx. Specifically, 1 shows that see closed path c, gamma of alpha d alpha equal to 0. Gamma of alpha d alpha equal to 0 for suitable closed curve c by writing closed path c gamma of alpha d alpha is equal to closed path double integral. The closed path c double integral. One path is closed, other integral should be running from 0 to infinity x to the power of alpha minus 1 e to the power of minus x dx d alpha. So, and then using the Pipin's theorem to justify the changing the order of the integrations, getting 0 to infinity one value, the other integrations, one integration run from 0 to infinity, other integrations, the closed path c, so gamma function x to the power of alpha minus 1 e to the power of minus x dx d alpha. So if we change in the order of integration, we get d alpha dx we get. So is equal to first integral is 0 to infinity e power minus x. The second integral of closed path c x to the power of alpha minus 1 d alpha dx. So then one uses the analyticity of alpha tends to x to the power of alpha minus 1. So then one uses the analyticity of alpha tends to x to the power of alpha minus 1 to conclude that. So the closed path c, integral of closed path c, x to the power of alpha minus 1 d alpha equal to 0. That's all. So hence the double integral above is 0. Similarly, in the case of the zeta function, the Weierstrass M test justify the interchanging the integral along the closed curve and the sum. This is the in infinite sums and integral form by using gamma and Weierstrass theorem and Pepin's theorems giving relations. What is double integral values? We get that. So this is a simple form in the Morse's tools in complex analysis. So the Morse's theorem is very applicable in the field of a complex analysis. So almost involve non-algebraic constructions. So involve what are even familiar algebraic constructions means addition, subtraction, multiplication, division, like. But this is the Morse's involve non-algebraic constructions in holomorphic functions. We know holomorphic in the definition of holomorphic. We take f1, f2, f3, a sequence of holomorphic functions, then applied in this Morse's theorem, suddenly is Cauchy theorem is followed. That is